Hello. My name is Virginia Bode, and this is videobeaux. This is the bad contrast program mode. Contrast is the difference between brightness and color on different parts of the screen. This mode applies this theory, but makes it bad. I hope you enjoy it. Try it out now.
The air moves backwards and forwards like that across a room, I would say, and moves in some kind of wave pattern across a room, and it will hit your eardrum and vibrate something which turns it into some kind of electrical signal which your brain decodes, and you go, oh, that's that note or that's that note. When we come to get that sound into a computer, the simplest way would be to have a microphone which basically turns sound into some kind of voltage. Really badly drawn wave like that. But what I'm interested in is how once that voltage gets down the cable, you can put it into something like a sound card. Here's one that I've got sitting up here. I've actually got a few lying around, and they convert what would be an analog signal, something coming through a guitar lead or a microphone cable, and they'll turn it into something that a computer can use, which is basically ones and zeros, a digital signal. There are two numbers that you associate with a wave file, one of which is called the bit depth, and then you've got another thing which is called the sample frequency. So basically these are the two parameters you use to convert an analog signal to a digital signal. I'll start with the sample frequency, the one I wrote down second, and that is basically the number of times per second that the computer will stab in and go, what is this level here? So if we say, there's a number of different levels, 1 going up to whatever, this axis here is time, and it will go across here and stab in there and go, that's the level at that point, and that's the level at that point, and that's the level at that point. And it will record these as numbers, so you might get like 5, 6, 8. So the number of slices per second that it does is the sample frequency. And obviously, the more of those you put in per second, in theory, the better quality the audio is going to be. Now, for a big wave like this, you don't need a particularly high sample frequency, because what you're getting there are tiny little details. You could probably stab in 2 or 3 times in each cycle. But obviously, if you start to get a wave that's much more like that, if you only sampled there and then the next sample you took were there, you're going to miss all of that data there. It's just going to end up cutting off what you would consider the treble, all the high frequencies, so the higher notes would just be cut off. I'm talking about physical high frequency data.
So we're talking about
high notes, like screechy notes. If you run you have 2 bits of glass scraping against each other, it produces a really high frequency which hurts your ears. That is a real top end note, and something that's like a real low sonic boom sort of note, that's a real low frequency because it physically has a longer wavelength, and the high-end frequencies have a really short wavelength. Now, we only hear up to around 22,000 hertz, so we call that 22K. But there's the 2 main industry standards that are used are 44.1K and 48K. And when I say K, that's 1,000 cycles per second. I'm going to put in the kilohertz there. So the reason that 44.1 was initially chosen...
Because it's a strange number, that, isn't it? 44.1. I mean, where does that come from?
Basically, the highest that they measured at the time, I mean, I don't know the exact science of this, I'll probably be corrected, but the highest that people thought people could hear was 22,050 hertz. And to get the full cycle of a 22,050 hertz wave, you need to double the sampling frequency. They picked 44,100 hertz as the sample frequency to be able to recreate anything that we can hear as human beings. For various reasons, that got changed for video. So CDs and audio MP3s and other such things generally come out, CDs definitely do, and MP3s most of the time come out at 44.1. And if you put a DVD or a Blu-ray in your player, you will be listening to audio at 48K. So computers and other devices, digital hi-fi amps, other stuff like that, need to be readily available to convert between those. Now, there's other people nowadays who use 96K. Some microphones can't hear as high as the human ear, so maybe they're not picking anything up above 16K. So sampling at 44.1 or 48K is well above what you need to pick up the sound from that particular microphone. Now the second thing is the bit depth, and the bit depth is the one that to me does make quite an important difference. So when you get a final product on a CD, or you get it on a DVD or a Blu-ray or something like that, most of the audio is at 16 bits, which basically means that between the top level of the plus here and the bottom level of the minus there, the levels that you can have, the different volume levels that you can have, you can only have at 16 bits, 65,536. You'd think that's enough different levels, but realistically it's kind of half that, because you're dealing with a wave here. It comes down below the center line and comes back above. So really you're getting half of that and half of that. So you get half of 65,536 above and half of that below, with the zero line in the middle. So you probably think that 32 and a bit thousand, I'm not going to do the exact maths, 32 and a bit thousand levels would be enough. And for a final piece of finished music that is kind of mastered and ready to go out, it probably is, which is why we get, that's the CD standard and that's the DVD standard. But when you're actually dealing with the individual instruments, you might end up with a drummer who's playing really loudly and hitting away really loudly. And then right at the end, he's just doing a little cymbal swell. And there's the tiniest little amount of volume going on, and you just want that volume to stay right to the end till the cymbal stops ringing. And unfortunately, when you're dealing with those raw files that haven't been mixed and there's not a lot of other things going on, if you record at 16-bit, you can really hear it being grainy, because it's all very well saying when you're dealing with a wave that's like that, you've got loads and loads and loads and loads and loads. I mean, you could have 32 and a bit thousand levels there to deal with. But if the wave that you're dealing with suddenly becomes only that big, you're only dealing with that amount of the space.
So this is maybe the drummer hitting, I don't know, a cymbal really hard there at the beginning.
And then it dies out, yeah, and 10 seconds after he's hit the cymbal, it's died out and it's become really quiet. And you want to pick up that noise as perfectly as possible without it becoming distorted and fuzzy, because what ends up happening is you end up creating a wave and you get all these points, and then when the computer puts it out, it puts them as points, and then it's got to draw lines between these points. And if you haven't got enough levels, you end up with effectively square waves, which don't sound particularly nice. They say zzz, you get quite a buzzy sound to them. So if you hear right on the end of a fade out of a track and you turn it up really loud in your hi-fi, you might be able to hear the song starting to get a bit zzz and a bit zizzy and a bit fizzy at the top end. And that's effectively what's happening here. So when you're doing recording, if you're trying to record a drum kit and then a guitar and then a vocal, and going through and actually layering it up as a song, you generally want to be recording at 24 bits. So for a 24-bit signal, we end up with 16,777,216 different levels, which is why on a professional level you record everything at 24-bit and you do your mixing, and generally within the audio software it passes it from one place to another. Actually at 32 bits you've got even more headroom to move.
So headroom's like space?
Yeah, space, because let's say you've got a wave there and then you've got another wave here, and you add the two together in a piece of software, it's going to produce a wave that's a lot bigger. Now, if that is hitting the top and the bottom there, and that's hitting the top and the bottom there,
what does happen?
What ends up happening is they get squared off. You'd add them together, and that might be bigger like that, and then that would just be cut off the top, and that'd be cut off the bottom, because these become no-go areas for the software, because you can't get a number that's bigger than the amount of bits. So you end up with a wave that's like that, and then it squares off, and then it comes down, and it squares off, and then it goes back up, and it squares off, and it sounds distorted.
So should we give one example of how that might sound? So I'm going to get you to say hello.
Hello.
Right, so that sounded horrendous in my ears.
That's called digital clipping. When you use a digital audio workstation, you're summing together wave files constantly, because you might have a bass drum mic, a snare drum mic, a hi-hat mic, 2 or 3 tom mics, 2 overheads, 2 room mics, a bass guitar, 2 guitars, vocals, whatever. So you could have 24, 36, however many, 50 odd tracks of information and with backing vocals, and you're summing them all together. And the idea being is, if you've been a good engineer, you will have recorded them with enough level that you're not keeping the level like that, because you don't want the level really small because it will sound grainy, as we previously discussed. But you want to send them in with enough headroom as well so that they don't clip. But when you sum all these things together, if you've got things that are only a little bit off the top, suddenly you're going to produce a signal which is far in excess of what 24-bit is capable of doing. So internally within the programs, they're passing the wave files at 32-bit to make up for the fact that you're summing these all together. And then the idea being is some piece of software at the end will show you that it's clipping, and you put in a plug-in and turn the whole volume down on the whole thing to get it back. So your final output ends up still sitting within the boundaries of what 24-bit is. Now, realistically, if you go the tiniest amount over what it is and you get the tiniest amount of digital clipping, you know, if you were recording a drum kit and one snare hit goes slightly over, you're not going to stop the whole recording. But if you were recording a guitar and all the way through the whole thing was just squaring everything off, it might sound pretty nasty. So you have to make these kind of fundamental decisions. What is going to be your sample frequency and what is going to be your bit rate? And generally for most applications, you'd be using 24 bits and 48K or possibly 44.1. You end up with all sorts of annoying artifacts when you're converting from one thing to another. You're either downscaling or upscaling. You're either throwing away data or you're adding in data and you're having to artificially make the data. So converting between 48K and 44.1, vice versa. It's not the bulk stuff you hear, it's the cymbals and the real high-end frequencies, the treble stuff. That's where you're going to lose the detail by doing that. But there's great algorithms out there that do all that kind of stuff. I don't. I just run it through my software, click the button, it does it.
We'd like to thank WhisperSync for Voice and Amazon and Audible Innovation for sponsoring this episode of Computer File. Do you wish you had more time to read? You know that point where you're really at a good bit in the book, but somebody rings or a reminder goes off or your alarm goes off and you just have to leave? Well, WhisperSync for Voice means you can stop reading and switch to listening to your book at exactly the same point that you've just left off. Find out more at amazon.com/computerfile. When you buy the Kindle book, you just select Add Audible Companion. You can add narration to over 60,000 Kindle bestsellers and popular titles. Just check out amazon.com/computerfile for the full list. Thanks once again to them for sponsoring Computer File.
This, and your is what would normally be your compass heading. So it's your magnetic compass heading. The phone can detect all of those aspects. The trick is then how we pass information to the plane itself.